Hi, we're Team IGT, and this is our project TouchPoint Companions Modeling Digital Twins. Our technical directors are Robert Corvasi and Raymond Leland. Our team is composed of Sean Kramer, Computer Engineering, David Delgado, Electrical Engineering, and myself, Ryan Holtquist, Electrical Engineering. First, a little bit about the company. IGT is a global leader in gaming technology. They go into jurisdictions all over the planet and provide hardware and software for lottery needs. They also do maintenance on the terminals as well. The two terminals they have are point-of-sale devices and self-service, such as that large standing up one you'll see at the bottom of the screen there. Our project is to work with one of these point-of-sale terminals, which process online wagers. Their contracts can last up to 20 years, so the likelihood of some sort of failure with these terminals is rather high. And IGT would like to have more data on their terminals in the field so they can learn more about them. The anticipated best outcome of the project is a fully functional digital twin that makes use of telemetry currently being collected by IGT, as well as telemetry added from sensors that we put in. Then the goal was to upload this telemetry to Amazon Web Services for analysis. The anticipated best outcome was not achieved. However, our team feels that it is very close and would be easily doable for a future project. The link to AWS was functional on our test terminal, but we could not get it to work on the one installed with the sensors. However, as stated before, we believe that it is not far off. The potential economic impact for IGT of this project is increased awareness of their terminal health, which will allow them the potential to fix problems before they occur. IGT faces significant economic penalties if their terminals fail, so it is in their best interest to keep them running as long as possible. It would also increase consumer confidence in their products and services as well. So here's an overall project block diagram. We have their main components are the terminal itself, the sensors, and then the link to AWS. And I'm going to talk a little bit about mostly the hardware and the sensors. So the first thing we accomplished was the actual testing of our sensors. We had 3 primary sensors, a DC current sensor, an AC voltage sensor, and 3 vibration sensors. The vibration sensors are used in different locations on the play slip reader itself. They're located on the side of it, stacked vertically, right where the gearbox is. The play slip reader is a device that takes in a play slip, reads it, and then spits the ticket back out. Another accomplishment we have is converting our AC waveform from the AC sensor to RMS. If you know your typical AC voltage waveform from a wall socket, it's going to be a 60 hertz signal that peaks around 169 volts and bottoms out around negative 169 volts. And we need to convert this to an RMS number, which is the standard used for AC voltage. This was rather difficult as we needed to take samples of the data and then calculate it from those samples using the formula for RMS waveform. After getting these values, we tested the terminal with the Variac variable AC voltage generator. We were interested in seeing at what voltage the terminal would cut out, and we figured out that the terminal could actually run all the way down to 55 volts AC until it shut off. The Variac also allowed for testing of the AC voltage sensor. You saw on the previous screen the fluctuations. That's what was occurring there. We were simply moving the dial around to test different voltages. After having all the sensors working, we needed to integrate them into one Arduino program. The Arduino is only capable of running one program at a time. But for telemetry collection, we needed to have all the sensors accessible at once. So it was necessary to take all of our separate Arduino files in sensor collection and put them all into one for the Arduino to run so it was able to access data from all of the sensors at once. And the terminal, the way we collected the sensor data was that it had a standby loop and a data collection loop. The standby loop would simply detect when there was a spike in current draw, which indicated that the play slip reader was active in taking in a play slip. That relates to the improved proof of our hypothesis. Last semester we used multiple play slips to simulate a dirty play slip reader. And instead this time we actually obtained a dirty playslip reader and tested it itself. As you can see, based on the graph, the clean playslip reader drew significantly less current than a dirty one. Or, in addition, we took the dirty one and put some sawdust in the gearbox to simulate increased resistance, and that while it didn't increase a significant amount of current draw, it stayed around the same and was still above what a clean reader showed. We also have to save this data to a CSV file because that's the easiest type of file to perform data analysis on that we found. And it was not able to be done directly from the Arduino, but we were able to accomplish this from the terminal window, get all the data from the 5 sensors total, and then save them to the CSV file for analysis, such as for that graph you saw on the previous slide that originated from one of the CSV files. I'm now going to pass it along to David Delgado, who's going to talk some more about the hardware.
In order to put everything together, we needed to make a wiring diagram of the entire project. This schematic is the full hardware wiring diagram to your right. It includes the pinout of the Arduino and each sensor, and it shows how they are wired together. It also contains the pinout of the connectors and displays how everything is hooked up to the actual terminal. You can see how everything is hooked up together by looking at all the connections displayed. And as you can see by looking at the diagram, the purple is the connectors, the orange is the sensors, and the blue is the Arduino, with the bottom right being the reader power connector. After the wire diagram was done, we followed it to wire all the sensors in the box together. The box is where we placed all the sensors and wires used on the project. Inside contains the proto board with the vibration, DC current, and AC voltage sensors, along with the Arduino. Coming out of the box are the wires for all the sensors, and we even hooked up AC outlets to it so we can power up everything just from the box, making it very convenient and presentable. It was neat and clean and a way to make everything portable. A high-level document, or HDL, is a document that contains all the information on a project. To keep track of our progress and to be able to have someone else continue our work, we needed to make a HDL. This document holds everything from stakeholders, scope of project, business requirements, technology requirements, risks, and etc. This document also includes the entire architecture of the project with descriptions of everything used. If anyone wants to know everything about the project, they can find it in this document, and that was the purpose of it. Here is part of the table of contents where you can see what type of things are included in the document. And now I'm going to pass it to Sean to talk about the software aspects of the.
So after we were able to collect all this data from these sensors that we had added, we wanted to find a way to get the data from the sensors all the way to AWS. The IGT terminals are currently running what is known as the Mosquitto MQTT message broker. MQTT is a lightweight messaging protocol that's used for things in the for small sensors and mobile devices, and they're optimized for high latency or unreliable networks. So it's a perfect protocol used for our instance where we want to send sensor data from a terminal up to the cloud. Mosquitto is a broker that enables sensor data to come through the terminal to the cloud. So the goal was Mosquitto runs locally on the terminal, and the goal was we needed to link the broker on the terminal, the Mosquitto broker on the terminal, to AWS, so that any messages that were posted to the local Mosquitto MQTT broker were then sent from that broker to a broker that exists on the AWS side, where it could be processed and examined for abnormalities. Bridging Mosquitto to AWS was a little tricky. To bridge the local Mosquitto broker to AWS, first we needed to figure out how to register the IGT terminal with AWS securely to allow the communication to occur. AWS is a very secure system, and learning AWS in the matter of months was quite challenging. But we were able to link these two brokers to see some data flowing. We then, to link the two brokers, a configuration file needed to be written very carefully that allowed the connection to be made between the two brokers, and that permitted it on both the AWS side and on the IGT terminal side. They needed to know about each other in order to have secure messaging occur. And once we were able to configure both brokers correctly, any message that was posted to the Mosquitto broker on the terminal was then forwarded to the AWS broker on the AWS side. Getting collect D to publish to the local Mosquitto broker was the missing link of our project. We were able to get the test messages that we manually were posting to the local Mosquitto broker on the terminal to AWS. However, we need the collect D readings, which were all our sensor information is stored, to also be publishing to the local Mosquitto broker, as collect D is the daemon that runs on our terminal collecting all the telemetry. Getting the collect D output to the Mosquitto MQTT broker was very challenging. However, we do think that with a little more time and collaboration, we could have been able to get this done. Unfortunately, we just ran out. But if this were to have been achieved, all sensor data would have been able to be visible on the AWS side. So the fact that we were able to show manually published test data to from the local Mosquitto broker on the AWS side means that we were just one small step away from our ABO, our anticipated best outcome. And at this time, we would like to take a moment and acknowledge our sponsors and everyone else that's helped us on this project. Thank you all.